So we can apply what we know about the fundamental theorem of calculus and the second fundamental theorem of calculus to discover some very basic formulas that are fundamental to physics. And that would be the formula for motion of a particle under a constant gravitational acceleration. So the whole idea is, let's say you have the Earth, we have x, so let's say x of t represents the height of the particle as a function of time. Okay, so we have just some particle that can move up or it can move down, but it's acted upon by a force, and the force is downward, and the force is equal to the mass of the particle times the gravitational acceleration. So g is equal to 9.8 meters per second squared in metric units, and it's equal to 32 feet per second squared in English units, which means that for every second of motion, 9.8 meters per second is added to the particle's velocity. So I have a drawing here, so I'm representing x as being the height, so x is pointing up. So the actual direction of the acceleration is downward. So g gives the acceleration, and then of course the force is just the mass times g. And force is equal to mass times acceleration, so in this case the force is equal to minus mg, but of course the force is also equal to the mass times acceleration, so the acceleration is just minus g. So what we have is we have a of t is just equal to negative g. So we have a constant downward acceleration. And we want to find a formula for the height of the particle as a function of time. Okay, so we'll start off with just a of t is equal to minus g. And so the idea is, well, let's integrate this to find the velocity. So the velocity as a function of time, there's a couple ways of doing this. So here's the fancy way using the second fundamental theorem of calculus. What's going to equal the initial velocity plus the integral from 0 to t of a of s ds. So what does this represent? This represents the initial velocity. Now if I integrate the acceleration from 0 to t, this one gives me the total change in the velocity between time 0 and t. So it's the total change for the velocity between the initial time and time t. If you think about this, the velocity is the antiderivative of a, so if I were to integrate this, I get v of t minus v0. So this is basically, we have the initial velocity v sub 0 plus v of t minus v of 0, and that's equal to v of t. So v of 0 and v sub 0 are the same thing, so that's exactly why it works out that way. Now, since a is a constant function, a of s is also just equal to minus g. So to use this formula, we get v of t is equal to v0 plus the integral from 0 to t of minus g ds. Now, if I integrate minus g ds, the antiderivative is minus g times s. Evaluated at t, evaluated at 0, we get v sub 0 minus g times t minus 0, or just v sub 0 minus gt. So the velocity as a function of time is the initial velocity minus g times t. That formula makes sense because for every second of the free fall, gravity is taking away 9.8 meters per second from the object's velocity. So we subtract an extra 9.8 meters per second from the velocity for every second of the free fall. If v0 is positive, that means the particle is initially going up, and it's going up at a slower and slower rate. Eventually hits 0 when t is equal to v0 divided by g. Then it starts coming down, just like that. So the velocity is the initial velocity minus g times t. Now we do the same trick to find the position. So the position is going to equal the initial position plus the integral from 0 to t of v of s ds. So this corresponds to my initial height of the particle. And then this, the antiderivative for the velocity is just the height or the position. So this represents the total change in the height between times 0 and t. Right? So this is literally x of t minus x of 0. So v of s, well, I just replace t with s, and I get v sub 0 minus g times s, which means that x of t is equal to the initial height plus the integral from 0 to t of v sub 0 minus gs ds. So if I just follow through with, so it's v sub 0 minus, the antiderivative is v sub 0 times s, integrating with respect to s, minus 1/2 g s squared, evaluated from s equals 0 to s is equal to t, so we get x sub 0 plus v0t minus 1/2 g t squared, and at the lower end point when s is equal to 0, I get 0 minus 0, which vanishes. So x of t is just equal to x sub 0 plus v sub 0t minus 1/2 gt squared. And that's the formula for the height of a particle as a function of time, as derived using the second fundamental theorem of calculus.